Wow, the screen so badly.
I know, right?
Oh, I paused the video. I paused the video. Oh no, I paused the video. Move it in front in case it's playing games. You mean why you playing games? Hey Regan, why you playing games Regan, stop playing games. Stop moving the tablet
He moved the second.
Okay, please take out the textbooks. Yesterday we learned about a kind of relationship or bond. We're going to go into a new one today.
Can I turn it a bit?
You can
still see
You should have done page 57 and more because we did more practice. Our class will have 2 less lessons than 06 because next Thursday and Friday there's no lesson. Yeah?
No.
I'll do my best to complete the syllabus. Tomorrow I intended for you to submit your homework, correct? No?
Homework.
I thought I'd give you a worksheet. RE. Yours is RE for the previous chapter on atomic structure, remember? I think we went through it. Yeah. You take out the RE. Someone, people need a sample to this one. RE 10.1 was supposed to be due tomorrow, but some of you already completed long ago. Okay, RE 10.1.
You put it.
Okay, I need to change the sequence a bit for 05 because we are missing 2 lessons next week. So good for you if you've not completed yet. You have more time to complete it. I will prioritize completing our syllabus first, then I'll go through the worksheet. So I may even, in the worst case scenario, go through when you come back from your September holidays. Okay, I'll prioritize completing syllabus, so if you want to start revision, you can start. Today, we're going to go on to a different kind of chemical bonding. But as with all lessons, we do a quick recap to connect everything so far. Yesterday, we learned that if we take a metal and a non-metal, we take metal elements and non-metal elements, and if we were to chemically combine them together, we will get ionic compounds. Okay, so that's one first thing we learned. We also learned that ionic compounds at the end of the day are made up of cations as well as anions. It is the attraction between each other that we refer to as an ionic bond. Okay? How do cations form? Cations form when they donate or give away electrons. How do anions form? When they receive electrons. And if you look at it as a complete picture, well, then actually the cations can just give away the electrons to the anions. That's how they end up attracting each other, because they are oppositely charged. Cations are the positive ones, anions are the negative ones. Okay, that's what we've learned so far. than that, yesterday one of the big portions of our chapter was also to learn how to write down chemical formula. As well as dot and cross diagram. We learned that in chemical formula, for example, if I write MgCl2, okay, thank you, that's called magnesium chloride. The number below, or the numbers at the bottom right hand corner, refer to the ratio of the elements in the giant structure. What is the structure of an ionic compound? All ionic compounds end up forming a structure that looks like that. It is actually super huge. Lots and lots and lots of ions coming together, attracted to each other. And so on and so forth. So you put dotted up because in reality, millions and millions of them come together. We have a problem like in the textbook we can only show a few because limited space in our page. In my simulation I also can only show a few because limited space. But actually millions of them come together to form a structure that is not only big, that's why it's called giant. Ionic, because what is holding and attracting them together is ionic bonds. That's what attracting them together. Lattice. Lattice means interconnected structure. Ionic compounds have giant ionic lattice structure. And it is in this structure that we want to know what is the ratio of the cations to the anions. That's why we write these small numbers at the bottom right corner. It just shows you the ratio. It doesn't tell you how many magnesium and chlorine there are, because in reality there are millions of them, but it tells you the ratio at the very least. Last but not least, you also learn how to draw a dot and cross diagram. If I were to draw a dot and cross diagram of this, you really just have to show me, number one, the cation with its charge, and number two, the anion, also with its charge. You should also show for the anion all the valence electrons and the electron in gain. Last but not least, the number at the bottom right hand corner, you will write it right beside the ion to reflect how many there should be for every one magnesium. Okay, so this is what we've done so far. We learned about ionic compounds, a relationship, a kind of bond between metal and non-metals. But we look at our periodic table goes something like that. Lots and lots and lots of them are metals. Lots of them are metals. But if you look at the other section, the non-metals, we have learned so far that metals and non-metals can form a kind of compound for ionic compounds. Today's focus, we're going to look instead just at one portion of elements. What happens if we combine non-metal plus non-metal? What kind of a relationship will they have? Because if you think about it, if we look at chlorine for example, if we look at chlorines have this as their dot and cross diagram. They are short of just one electron to be full. Let me look for another element, the non-metals, chlorine. Okay, and if you look at hydrogen is also a non-metal. Hydrogen only has one electron. It would like one more so that its outermost electron is full, right? So how? What can we do when we have non-metals and both of them also want electrons? I want it really badly. Right? We know non-metals like to accept electrons. Hydrogen also wants to accept the electron. If both parties want to only take how? What kind of relationship are we going to have? Hydrogen gate? That's actually not what happens. Hydrogen is a non-metal. So, yesterday we learned that in this relationship of ionic compounds is a give and take. One party gives, the other takes, and then both are attracted to each other. Today we look at a different kind of relationship. Maybe this is the kind of relationship you want to aspire to. Yeah? Both parties want to take. So how? What should we do? Here on the screen, I'd like to show you a simulation. I have two atoms. More specifically, I'd like you to figure out what are the two atoms here. The clue is that this atom only has one proton. So based on the periodic table, which element only has one proton? What is this element? What are these two elements they are putting on the screen? Megan? Hydrogen. Yeah? These are two hydrogen atoms. Don't believe your periodic table. Hydrogen atoms, atomic number is 1, only has one proton. It also only has one electron. So here I have two hydrogens side by side. I'm going to erase the rest because it's not focus today. We're going to focus on non-metal and non-metals today. Here I have two hydrogen. One hydrogen atom with an electron, another hydrogen atom with an electron. On the screen, you see two hydrogen atoms, same thing, except this time around you can see the electrons kind of swiveling around it. I'm now going to try to bring both atoms together. Watch what happens. Because in the previous example, one gives, one takes. But what do they do when you observe two non-metals? Okay, ready? What do you observe happening? Now I try to pull them away. What do you observe happening?
Pass the ball. Pass the ball.
Brian says they're both clinging to each other, kind of. Neither of them gave nor take. They're kind of just clinging to each other's electrons now. Let's look at it from another perspective. Here, again, I have the two atoms. Yes, I bring them closer to each other. You see this happen. Now, I add a line onto the electron just to show you the attraction. The line over here you see represents how the proton is attracting the electron to itself. But watch what happens as I bring the atoms together. You find that the electron from the other atom starts to get attracted by the one on the left. At the same time, the other atom on the right is attracting the electrons from the one on the left. Both of them are kind of just pulling on each other's electrons. There's no giving, there's no taking, it's in between now. In other words, what's happening between the two hydrogens? They end up not giving or taking, they end up sharing. Okay? Maybe we can all aspire to such a relationship. We share. Yeah? So when we look at non-metals and we put them side by side, neither of them will give up their electrons because both of them want electrons. That's what non-metals do. They want more electrons. But if we put two parties that both want, then they end up no choice, they have to share. That's the only way about it. And where do non-metals, what do we call such a bond? We call such a bond a covalent bond. Okay, we call it a covalent bond. Covalent bonds are when electrons are being shared rather than give or take. So which part of the textbook am I at today? I progressed to a new kind of bond. So I'm on page 60. By the end of today, you should be able to do page 61. Okay, I'm at page 60 now. Covalent bonding. You can see on page 60, in fact, I've already bolded some of the words. Covalent bonding, and you see they share their valence electrons in bold. Here I am on page 60, which requires the textbook to be opened first. Page 60. So which region of the periodic table do we find elements that want to share electrons? We find them here, the non-metals. Between non-metals and non-metals, they tend to share, because both of them want electrons. Do take note that even though hydrogen is not as part of this section here, for your periodic table, hydrogen is just floating on the very top. We consider hydrogen a non-metal. So you shouldn't be drawing instances where hydrogen gives away an electron. Okay, you shouldn't be drawing as such. Instead, you should be drawing hydrogen as a sharing kind of relationship. Okay, I'm going to skip some of these portions because it is out of our syllabus, so that I can bring us to the final portion. Okay, I'm going to now teach you how to draw the dot and cross diagrams and chemical formulas for covalent bonds. Okay, we know how to do it for ionic, right? Let's say I just give you magnesium chloride, same as just now. What you are able to do now is to draw ions, and then you show me how they give and take electrons. But how do we draw a dot and cross diagram or the chemical formula for elements that don't give and take, but they share? Okay, so that's the scope for today. By the end of the day, you will know how to represent a dot and cross diagram in the sharing form. Let's begin first with hydrogen. Observe that hydrogen has one electron in outermost shell. How many more does each hydrogen want to be full? Just wants one more, correct? This hydrogen just needs one more electron. Just needs one more electron for it to have a full outermost shell. This one just needs one more as well to have a full outermost shell. But there are no metals nearby to give electrons. So how? But we have two right here. So the way about it you can represent, how do we represent this sharing in the middle? We represent it in a rather neat way. This is what we do. We will just write the hydrogens, or the two elements side by side. To represent the sharing, we just put the two electrons side by side like that. Okay? This implies sharing. After you are done sharing, I want you then to do a quick count. Let's count up. For hydrogen, if we count the number of electrons on the outside now, how many does it have? Okay, this hydrogen now has 2 electrons. It is happy. Let's look at the other electron. Sorry, the other element. Okay, it is also happy because it has 2 outermost electrons. Okay, following? So I just show you a simple example for hydrogen first. What happens when you share? To represent sharing, draw the electrons just side by side as a pair. Let me teach you how to do dot and cross for various other elements. Sorry, so if this is the dot and cross, what would the chemical formula look like? Okay, the chemical formula will look like this. Just a H. Don't be an educated guess what I do next. I have to write 2 somewhere. Yeah? But again, we adopt the same convention. Right here at the bottom right hand corner. Okay? So this is the chemical formula for hydrogen. 2 hydrogens, dot and cross diagram. Right now we're try to draw more dot and cross diagrams for various other examples. So let's open your textbook. We look at page 61. Okay, page 61 shows you the hydrogen example. I'm going to run through how we will do the same concept with chlorine. Okay, let's look at chlorine. So I'm going to erase this away. Okay, let's look at chlorine. I'm going to draw two chlorines now. Now, I need you to follow me on this section because I think it will get challenging if I let you do the rest by yourself if you don't follow me for here. Okay, so boys at the back, following up. So, if we look at chlorine, let's draw the dot and cross diagram for chlorine first. If we have two chlorines side by side, 1, 2, 3, 4, 5, 6, 7. Agree? 7 electrons. Let's draw for the other chlorine. 1, 2, 3, 4, 5, 6, 7. How many more electrons does chlorine need to have a full outermost shell? Just needs one more, right? It just needs one more. Same for this chlorine here. Just needs one more. So if both parties just need one more, how many electrons should we share between each other? If both parties just need one more. Then we just share one each other. So observe, I'm going to just bring both of them close to each other now. And I do a quick sharing. Now let's draw the other electrons. 1, 2, 3, 4, 5, 6, and 7. So let's do step 2. Let's check if both elements now have a full outermost shell. So step 2. Please don't draw like I do. I'm drawing this cloud so that you can do a quick count. So let's look at this chlorine here. This chlorine here, let's check how many electrons does it have. 1, 2, 3, 4, 5, 6, 7, 8. It is happy because there's a full shell after sharing. Next one, this chlorine here. 1, 2, 3, 4, 5, 6, 7, 8. Also has 8 electrons now, full shell. Both are happy. And we are just sharing this pair of electrons here. How do I write this out in chemical formula? Just a simple Cl2. Following? Okay, so let's try the next example. It gets tougher and tougher. Everyone please complete chlorine first. If you look at the second row, there's chlorine. Could everyone do chlorine with me? Let's make sure you don't draw the circle. Okay, everyone do chlorine first. Then we'll go to the next example. For those of you that think you know how to do the next example, please go ahead. But you'll find that oxygen wants more than one electron. How do we share? Cl and dash here. I say again, everyone, do not draw in my clouds. I only draw in the cloud just so that I can count. But this is not what you're supposed to do. Your final diagrams should just look like that. I'd like to challenge all of you now. What about oxygen? What will two oxygens together look like? First and foremost, oxygen has how many valence electrons? 6. Are you all comfortable with that? You can get it now? Okay, 6 valence. So 1, 2, 3, 4, 5, 6. Imagine I have two oxygens. 1, 2, 3, 4, 5, 6. How many pairs of electrons do I need to share such that both will have 8 electrons in the outermost shell? Okay, so this is the next challenge. The clue is this. You can share more than one pair of electrons. You can share more than one pair. Should I get everyone to try? Try. If both parties need 2 electrons each, then how do we go about sharing? Both parties just need 1 each, so we just shared 1 pair. Now if both parties need 2 each, how do we go about solving this puzzle? Can I get everyone to try? I'd like you to try to think this through, and then after that, you will run through. You counted, right? 1, 2, 3, 4, 5, 6, 8. It's loading up. Joe? Computer? Good. Ah, you're trying a new one. Something's a bit odd, huh? This X, huh? The copy also never copy the same thing. Totally different from what's in there. Oh, but you see how when you share the electrons, right? How come the cross is on this side and then the dot is on the other side? How the cross to one side, not the dot on the other side? Oh, can there be 3 pairings? Huh? Okay. Why not? Yeah. But are you over to me? Yeah, I'm going to go through oxygen now. Let's look at oxygen. Oxygen has 1, 2, 3, 4, 5, 6 electrons. The other one also 6. Both of them need 2 more. So what can we do? Okay, so if you notice the trend so far, if both parties need 1 more, then we just share 1 pair. If need 2 more, we share 2 pairs. So, for example, if both oxygens need 2 more electrons, this is how can we draw the arrangement. Draw the oxygen side by side. I will first draw 2 pairs of electrons being shared. Then I'll draw in the remaining electrons left behind. So, oxygen here, if it's already sharing 2 electrons here, there should be 1 more, 2, 3, 4. So 1, 2, 3, 4, 5, 6 is what it originally has. Let's look at the other side. I should add in the leftover electrons. Then you count in total. Is there 8? There's 1, 2, 3, 4, 5, 6, 7, 8 for this particular element. And the other side also 8. Okay? So how many pairs of bonds have we created? We created two pairs. Right? 2 sharings. Okay, this is a gradual increase up. So if you're done with oxygen, try nitrogen next. Nitrogen, interesting. Nitrogen has 1, 2, 3, 4, 5, 6, 8, 5 only. It only has 5 electrons each. Both parties want 3 electrons. So how many pairs should we share? Do I get you to try it out for nitrogen? Those of you that are getting the drift of what's happening, you can even progress down to the subsequent examples where we try different elements. Yes, this one is correct. This one. Okay, are you got that? Yeah. See oxygen. Alright, okay. So nitrogen each has 5 electrons. Both in 3. So yeah, so if you need to share 3 pairs, then you just start off the same way. Draw 3 pairs first. Yeah. Okay, then you draw the leftover electrons. Yeah. Done. Yeah. Okay. So I haven't hit that stage yet, but if you notice, every line represents a pair being shared. Okay. Yeah. So okay. So how do you test? You count. So you count this nitrogen up. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So you decided to share 1 pair. Perhaps you share more. You go and try and error. How many more can you share? And maybe one way to go about it is both nitrogens, how many more electrons does it need to share? Remember when you share, one needs to come from the other, the other one is from the other. And then in the middle, we only put, you see, in the middle we can only put the sharing. We don't put extra in, there's extra one here. We represent hydrogen. So you see, the chemical formula is H2O. Alright, you draw hydrogen and oxygen. Yeah. Correct. Okay. Yes. Okay. As I walk around, I think you are getting the drift of it. For those of you that have trouble, let's look at nitrogen. Nitrogen has 1, 2, 3, 4, 5. It needs how many more electrons? 3 more. This one also needs 3 more. So how many pairs should I share? 3 pairs. Right? The number of pairs is determined by how many more we need. So 3 pairs. So let's start off. Let's erase everything away. Then really just start off with 3 pairs. So 1, 2, 3. This one electrons come from here. 1, 2, 3. We share 3 pairs. Then let's just draw in the leftover electrons. Let's count. Always do step 2 to count. So this nitrogen here is 1, 2, 3, 4, 5, 6, 7, 8. Happy already. Okay? So that's what nitrogen should look like. Okay. So far we've only been working with elements of the same kind. Notice I joined hydrogen and hydrogen together. Chlorine and chlorine, oxygen and oxygen, nitrogen, nitrogen. Let's start to take things one step further. What if we combine non-metals from different elements? Here I have 2 examples, hydrogen and fluorine, water. What will hydrogen and fluorine look like? Okay, what will HF look like? Hydrogen has 1 electron, fluorine has 1, 2, 3, 4, 5, 6, 7. How might they share such that both have full shells? Okay, so we'll be very tempted to draw ions because technically hydrogen can just give away the electrons, right? Yeah, but remember hydrogen is a non-metal, so we will use this sharing method. Okay, we share when it's non-metal. Okay. Okay, you are nearly getting there. Okay, so now this hydrogen, just put it on the other side. It looks more balanced, you know. Yeah. Okay, good. The H2O at the bottom is the ultimate challenge. Okay, H2O is the ultimate challenge. If you think you can do that one, I would say you're quite good to do. Okay, so here you're trying to share this dot, this one, right? So we make it separate at the middle, we only show them. So this electron will shift up there, so the teacher can focus and you know how many Okay. How to do this one? Actually, this one is pretty easy. We just need to bring it close to each other. Let's share it this way. This comes from hydrogen, this comes from fluorine. Okay? Hydrogen just needs 2 outermost electrons to be at a full shell. Fluorine needs 8. So this is the answer. How about water? Okay, the clue is this. You look at the chemical formula. The formula says H2O. So how many hydrogen should you have? How many oxygen should you have? Okay, could everyone try the last one? Water. For those of you that are bored and done, I have a chemical for you. You see if you can do this one. This one is quite challenging. This chemical is called ammonia, NH4. How to do this? NH4. The good news is that you will not see this in your exam. However, if you can do something so challenging, anything lesser is going to be easy for you. Yeah. Done? How's you lah? You're the only one not doing work. Joy is better. Always look unfocused, but actually he's constantly thinking.
Vegan ah. Vegan is enigma. Cannot tell what's on your mind one. Yeah. Sorry. Sorry. Yes. Yeah.
So 2.5 is
Okay, let's invite someone up to do for water, H2O. What? You want to do water? Ammonia one. Okay, sure. Oh, okay, Brian is going to help us do water. Let's see what Brian will do. Thank you. Okay, well done. Shall we do the same you always do for me? Thank you, Brian. Brian feels good. Feels good, I said. People clap for you. That's why you always clap for others. Okay, so we look at water. Whatever you do, always just double check. So let's look at hydrogen. Hydrogen has 2. Can. What about oxygen? 1, 2, 3, 4, 5, 6, 7, 8. Can. Okay, so what Brian says very good. He has shared very nicely. Everyone has the number of electrons they want. Have you all solved the puzzle? How to do NH4? NH4. Yeah? NH4. You want to do? No one can do. Yeah, I just realized I set you all up for failure. There's no way you could have done this. Yeah. Then, okay, sorry, I set you up for failure. There's no way you could have done this. Okay, yeah, sorry. Sorry, as I look at what you have drawn, right? Yeah, I realized there's no way. Do you know what's the mistake? Sorry. So, you may be trying very, very hard. So, you realize it's impossible to do that. But as you were trying to do my NH4, and you realize it's impossible to do, but you know what this means? You really have enough chemistry knowledge to know what can or cannot bind to each other and the proportions. If you were to put 4 times of hydrogen to every nitrogen, actually you will not get them to react. It needs to be a nice 3 to 1 ratio. Okay? So it's very beautiful. Once you know this kind of knowledge, you know what's the ratio of elements to use. You don't waste my chemicals anymore. So can you do NH3? Can I be NH3? Sorry, I'll show you how to do it. Okay? Okay, show you how to do NH3. Nitrogen has 5 electrons, it wants 3 more. All of the hydrogens just need 1 more. So what's the best way we can share? check is nitrogen. Let's have a count around nitrogen. Nitrogen is 1, 2, 3, 4, 5, 6, 7, 8. And truth be told, all of them have the same number of shells. Just one shell, you just need 2. Okay, so well done. This is how NH3 will go. Okay, I just want to let you know, for your year-end exam, we will not test anything else beyond this table. Okay? As long as you can do everything in this table for your year-end exam, you are good to go. I just want to let you know what can change from this table. For example, you look at hydrogen and fluorine. If I instead give you, rather than hydrogen and fluorine, I give you hydrogen and chlorine. Okay? It's the same thing. You notice? Hydrogen and chlorine versus hydrogen and fluorine. You will draw exactly the same thing, right? Because chlorine and fluorine are in the same group. So, what I'm telling you right now up front is that if you can do everything in the table on page 61, the only thing that will change now is I change the elements. But I will make sure I only use the same groups to replace. I don't know if you caught the ball. Okay? I say again, as long as you can do everything in this table, you are prepared. I will not test you up to 3 levels of bonding. Your seniors even know how to do this, Excuse me? Yeah? But this one is crazy, But your seniors have enough skills to do it. Yeah. But the way they join together is even crazier. So they join this way, Okay, I don't know if you know this now. Just one last section. You see the structural formula. How do we represent the bonds? If it is just one pair of sharing, we use one line. Every line equals to one share. Okay? So, for oxygen, where you share 2, what do you draw for oxygen? Just 2 lines. Every line represents a pair. Last but not least, for nitrogen, you share 3 pairs. Therefore, okay, you fill in the blanks. So how do we do for hydrogen and fluorine? Hydrogen, you share 1, so like that. H2O, how to do H2O? Oxygen, and you branch out 2 lines. Okay, so every time you see a line from now onwards, it represents a pair being shared. So what does this look like? So your seniors know it to be like that. When you teach JH3, this is what it looks like. C, C, okay, actually the carbons join the ring. Right. And then after that, each one has a hydrogen coming out.
Yeah, but hexane too.
And so on and so forth. So it gets really complicated. There are many ways to join chemicals together. Okay, how? Doable? Yeah? So far we've learned to draw dot and cross for covalent as well as ionic. You can expect that come the end of year exams, we want to test your ability to be able to draw dot and cross. But I won't tell you who is metal, who is non-metal. You have to figure out yourself from the periodic table. If I give you 2 non-metals, you have to tell me whether it's covalent or non-covalent. Or ionic. So before we end up today, last 5 minutes, let's do a quick test. Because honestly, you end up drawing the wrong thing if you don't know how they bond with each other. I would like you to draw a dot and cross diagram for these 2 different compounds. First one, I would like you to do. Okay, but I'm not going to tell you which one is ionic, which one is covalent. You figure out yourself. So first one.
What's that?
Okay, is that ionic? Is it covalent? Will you give and take or will you share? Okay, please do the dot and cross for me. Next one. Okay, I have two on the whiteboard. Figure out yourself which one is covalent, which is ionic. Draw the dot and cross for these two. Okay, that's where we will end off today. Please draw the dot and cross for these two. Is it covalent? Is it ionic? Draw the dot and cross diagram for those two compounds. You want to challenge yourself? You wait to see why that's only complicated. The day, right? Okay, you ready? Are you ready for the table? Yeah, that's for you to figure out. So between these two pairs, which one is the ionic, which is the covalent? Dot and cross. How do you tell? So much speed. Okay, I will lay on some clues for you to figure out the dot and cross. This is a metal. This is a non-metal. 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 Okay, so draw the dot and cross accordingly. And you see, if you don't know which is ionic, which is covalent, you actually end up drawing the wrong kind of dot and cross. Yeah? And you realize you hit a dead end. So it's very important to know which kind of dot and cross to draw. When do we share? When do we give and take? Yes. Yeah. So how many hydrogens do we need? So you need one more hydrogen. Okay, ready there. We forgot the chart. Where's our? No, good. Good, we figure out that you actually need to. For those doing hydrogen and sulfur, just a clue. Actually, you need more than one hydrogen. Okay, one hydrogen is not enough to solve this puzzle. Sulfur needs 2 more electrons. Hydrogen can only offer up 1 to share. So actually you need more than 1 hydrogen. Yes, but always keep a metal first.
Yeah, you're moving back.
Okay, that's all for today. Tomorrow I'll just quickly get one of you to draw the answers on the whiteboard. Okay, so finish this off. Tomorrow I'll get 2 individuals to draw their dot and cross. Okay, thank you. class.